The previous video defined stability and the criteria for stability of control systems. And we characterize any system, and by system, I really mean the transfer function, into one of three categories: stable, marginally stable, or unstable. It's stable if all the poles of the transfer function are strictly in the left half of the complex plane. Unstable if any pole is in the right half plane. Marginally stable if the rightmost poles are exactly on the imaginary axis and not repeated. And it's unstable if those rightmost poles on the imaginary axis are repeated. So let's do some examples. And these pictures came from an old exam of mine, and the students didn't do that great on it. Just these pictures. Well, first, the X's on here are the pole locations. The O's are the zero locations of the transfer function of the system. All you need to look at, you can ignore the zeros. Just look at the poles and look at where the rightmost poles are. Here they're in the left half plane. That guy's stable. Here, just ignore all these zeros. You're looking at the rightmost poles. Again, strictly in the left half plane, stable. Here, up, as soon as you see a pole in the right half plane, it's unstable. That's a no-brainer. X over to the right of the imaginary axis, unstable. Here we got a zero over to the right, ignore it. But the rightmost poles are exactly on the imaginary axis. But there's just one X in each location. Those are simple poles. These poles are not repeated. That is what we call marginally stable. Here's the exact same picture, but now these guys are double poles at the same location. They're always going to come in complex conjugate pairs, by the way. This guy is plain old unstable. Double poles on the imaginary axis. Again, ignore where the zeros are. That confused a lot of students. If you weren't looking at the pictures of where they are in the complex plane, if you had, say, factored, these are the transfer functions, and if the denominators are factored, you can quickly spot the poles and know where they are. This guy's poles are at -1 and -2. On the real line, left half plane, stable. This guy's -1, this pole is at +2, unstable. Right half, this guy, right half plane pole means it's unstable. This guy got a real pole at -1. This is a complex pair of poles. Use the quadratic formula if you got to do the arithmetic. But the real part will be at half of this guy, half of +4. Well, since that's a plus, it'll be a -2. The real part will be -2. For the left half plane, stable. This guy, these poles are at plus and minus j, exactly on the imaginary axis, but not repeated. Just one complex pair of poles. So that guy's marginally stable. This guy has poles at plus or minus j, but that thing is squared, so it's a double pair. And by the way, they have to be at the same location. I might go back to this. If they weren't repeated here, but you had another complex pole up here and down there, that's okay. That would be marginally stable. What makes it unstable is poles at exactly the same location on the imaginary axis. What if it's not factored and it's something too big to try to factor? Well, there's a couple of sufficiency tests, actually necessary conditions. If this is your characteristic equation like this, all these coefficients must be strictly positive for it to be stable. That doesn't mean if they're all strictly positive, it will be stable, but it says if any of them are not strictly positive, it's at best marginally stable, but it's not stable. Couple of examples. Let's see. Let's say you're given this forward path transfer function, but in a unity feedback configuration. First thing you've got to do is find the closed loop characteristic equation. We need the closed loop transfer functions to do stability analysis. So how do I do that? I add numerator and denominator. S squared minus 8s plus 10. That's the characteristic equation. I don't care what goes on up top. Here's the characteristic equation. I see a minus sign there, so it's not stable. Actually, in this case, it's unstable, but it's certainly not stable. So I couldn't even compute a steady state error. That's the way this problem was posed. If it's stable, determine the steady state errors. Well, first you got to determine if it's stable. In this case, it's not. How about this guy? Numerator plus denominator, or denominator plus numerator. So here it is. Let's see, I've got an s to the fourth, s squared, s cubed, s squared. I'm missing s to the first power. There's a missing a. One of the a's is 0, remember? These guys must be strictly positive. 0 doesn't count. Guy has a 0 coefficient, so he's not stable. Could be marginally stable, but he's not stable. So what if the necessary condition is satisfied? You haven't ruled out stability, but it might not be stable. Then we've got to do this thing called Routh-Hurwitz, and I'll get into that in a subsequent video. This is a whole sort of tedious technique to see where the poles of the system are, or at least determine if any are in the right half plane, or left half plane, or maybe on the imaginary axis, and how many there are. So we'll cover how to tabulate Routh's array, and from that determine all these wonderful things. Stability, number of poles in the right half plane, etc. We'll get into that later. So to summarize, we define stable, and by that we mean a bounded input guarantees it's stable, it guarantees a bounded output. Unstable bounded input yields unbounded output. Marginally stable, you get sustained oscillation, but it can be unbounded output if the input is a sinusoid at the same frequency. And it's determined completely from the poles of the closed loop characteristic equation. Stable if all poles strictly in the left half plane, unstable if any poles in the right half plane, unstable if the rightmost poles are on the imaginary axis but repeated, and marginally stable if the rightmost poles are on the imaginary axis and simple. With that, in the subsequent next video, we'll start on Routh-Hurwitz.